This video is about understanding limits, and I'm going to use a commonly known problem, which is the tangent line problem, to explain explain the concept of limits. Now, first we've got to understand what a tangent is. So, or a tangent line. Note that this tan is completely different from the trigonometric tangent function. Suppose I have a curve, just that, and the tangent is a line that would touch the curve exactly at one point. For example, that. And it has to be going in the same direction as the curve itself. For example, you have a tangent line there, perhaps it would go something like that. So it touches that one point, goes in the same direction as the function. In other words, the function's increasing, the tangent line is also increasing. A secant line is one that is going to pass through two different points. So that is the tangent line, and that is also the tangent line. If I drew a line of that sort, it touches at 2 points, and that is what we call the secant line, or simply the secant. Now, suppose I have the function, say, y is equal to 2x squared, which is nothing but a parabola, and it is going to be open upward. The vertex is at 0, and that is our function. Now, I'd like to find the tangent, say, at P, some point P. I'd like to know the tangent right over there. And let's say that point P, when x is, say, 1, y is 2, so the point would be 1, 2. So I'd like to find the equation of the tangent line at P 1, 2, or P is the point, and that is 1, 2. Now, what is the problem? There is a huge problem. If we have to find the equation of the line, one would need 2 points. Unfortunately, here I have only 1 point. So how do I find the line? Should I just give up? No. We have to use the secant line and approximate. Now, how do I do that? So a secant line is going to pass through 2 points. So I'm going to pick another point. When x is 2, y would be 2 times 2 squared, which is 8. So 2 and 8. So I'll call it 2, 8. So I have 2 points, and I'll call that point as Q. So the first point is 1, 2, the second point is 2, 8. A more generic approach would be to pick an arbitrary x. Pick arbitrary x. Instead of 2, 8, we'll just have an arbitrary x, and the corresponding y would be 2x squared. Now let me call that to be r. R would be my point, which is x comma 2x squared. When the value of x is some x, the corresponding function value is 2x squared, value of y. So the first point is p. I have p, which is 1 comma 2, and the second point is my arbitrary point, p and r. Now on the sides, I am going to find the slope of the secant line, just to demonstrate, using points p and q. So we have the slope, which is y2 minus y1 over x2 minus x1. You'll get 6 over 1, and we get 6. That is the slope of the secant line. And we could find the equation of the line by using the point slope formula. Y minus y1 is equal to m times x minus x1. And I'll pick one of the 2 points. For example, I'll just pick p. The slope is 6 times x minus 1. So y minus 2 would be 6x minus 6. Y would be equal to 6x minus 6 plus 2. Y would be 6x minus 4. And that is the equation of the secant line. Now, we want to find the equation of the tangent line. So to do that, I am going to find the slope of these 2 points. y2 minus y1, 2x squared minus 2, divided by x2 minus x1, so x minus 1, and the 2 in common, x squared minus 1 over x minus 1. And I could actually simplify this. I could write x squared minus 1 as x plus 1 times x minus 1. If you FOIL, you will get x squared minus 1. Those two would get cancelled, and I'd have 2 times x plus 1. So I have found the slope, and if you notice, this slope varies with respect to x. Now, I want to move this x. If we go back to our curve, my point P, which is 1, 2, is right over there. I've picked some arbitrary x, let's say r, x, 2x squared. I would like to find the slope of the tangent line using the secant line. So as I move r closer and closer and closer in that direction, I'm likely to get to meet the point P. I know the slope between P and R to be 2 times x plus 1. Now my job is to change the value of x, which is right over here, the value of x, and that is 1. I'm going to bring x really close to 1. And if I did that, I am going to get a corresponding slope at P. So let's see. The value of x and the slope PR. Now, I know if I pick x as 2, the point was 2 comma, it will correspond to the point Q. So the slope in this case, since this is 2 times x plus 1, by plugging in I'll get 2 times 2 plus 1, which is 6. Notice, this is nothing but the slope of the secant line connecting P and Q. And recall, Q is 2,8. So since R is arbitrary, I could pick any value. Now I want to bring this really, really close to 1. So I have picked X to be 2. I'm going to move it really close to 1. Let's plug in 1.5. So 1.5 would give us 2 times 1.5 plus 1. It's going to give me 5. Let's plug in 1.1. Have 1.1 plus 1. I'll get 2 times 2.2, which is 4.4. And 1.05 be 2 times 1 plus 1.05, and that slope would now become 2 times 2.05. We could use a calculator here. 2.05 times 2, I get 4.1, and 1.005 would give us 2 times 1 plus 1.005, and that is 4.01. So I am getting really, really close to 1. Started at 2, I'm picking values, getting really close to 1, and of course if I plug in 1, I am going to get a value of 4. As you can see, these slopes approach the value 4. So as you move x closer to 1, the slope moves closer to 4. So a rational guess, the guess for slope at P exactly is 4. So now I know the slope at P, which is 4, so I can find the equation of the line or tangent line at P. So the point P is 1,2, so I have y minus 2 is equal to 4 times x minus 1, because the slope at P using limit. So y minus 2 would be 4x minus 4, y would be 4x minus 4 plus 2, so y would be equal to 4x minus 2. That is the equation of the tangent line at P. So if you think about it, each of these points, the values of x that I've chosen, corresponds to the slope of a secant line. So each of these values right over here is nothing but the slope of a secant line. So as you change the values of x, as you bring it closer to 1, which is the tangent point, the slope of the secant lines approach the tangent. So the note here is the limit of slopes of secant lines is the tangent line slope, or slope of the tangent line. So that is the takeaway from this particular application. Now there is another application which involves the distance with respect to time when you drop a particular object from some height. So it is given by Galileo, and this is the expression. this is nothing but the distance at time t of a free-falling object. So suppose we would like to know the velocity of the object. Suppose we want to find the velocity of the object, of some object, dropped from my height of 20 meters. It has to be in meters because this expression holds true from in meters. So height of 20 meters, you're dropping the object, and at time t equals, let's say 3 seconds. Notice this is an exact or instantaneous time. So at some arbitrary time, the distance would be s of t, and we are trying to find the time at 3 seconds, or the velocity at 3 seconds. So we know velocity is distance over time. Now, if I pick two different time intervals, say for example, I pick t equals 2.5 and t equals 3, I'm picking two different time points, then I would have a corresponding distance at 2.5 and at 3. So the distance over here would be 4.9 times 2.5 squared minus 4.9 times 3 squared, or the other way around, so minus and plus, over 3 minus 2.5. So that would give us 4.9 times 3 squared minus 2.5 squared over 3 minus 2.5, which is 0.5. I could go ahead and compute this value. 3 squared minus 2.5 squared times 4.9 divided by 0.5. That gives me a velocity of 26.95 meters per second. Now mind you that this is a value that I obtained by selecting two fixed time points, but I would like to find the velocity at an instant of 3 seconds. Well, of course, one could plug in the value 3 and guess it, but we are trying to demonstrate the concept of a limit. So how do we do this? Just like the previous problem, we're going to pick an arbitrary time point, pick an arbitrary time, let's say capital T, and time t equals 3. So velocity now would be equal to 4.9 t squared minus 4.9 times 3 over t minus 3. So the curve is going to be a parabola, the distance curve. This is s of t. So what I'm doing is I'm picking a value capital T for time, and I'm picking a value 3. I'm going to move this t closer and closer to 3. Of course, it can't equal exactly 3 because you get infinity when you type 3 in. So 4.9 times t squared minus 3 over t minus, oh, that is actually 3 squared. 3 squared t minus 3. Just like the previous problem, this is going to become 4.9 times t plus 3 times t minus 3 over t minus 3. Get cancelled. You'll get 4.9 times t plus 3. Let's pick values of t and make this velocity. This velocity is nothing but the slope of the secant line that is connecting 3 and t. So these 2 points right over here, that's our secant line, poorly drawn of course. And it has a name, it's called the average velocity. Because we are looking at the slope of the secant line. And now I'm going to pick some number, say 4, and I'm going to move it closer and closer toward 3. So I'll start at 4, I'll pick 3.5, 3.1, 3.05, 3.005, and 3.001. And let me find the velocities for each case. So the velocity would be 4.9 times t plus 3. So when I plug in 4, I would get 4.9 times 4 plus 3, which is 7. There is an efficient way to do this using your calculator. So to do that, let's go ahead and define the function. Our function would be 4.9 times, instead of t I'm going to use x plus 3, and second mode to quit. Now press second and go to table set. We'll start at a value of 4, and you can ignore the change in table. That is the value with which you increment or decrement the value that your values that you're going to use in the equation. So I am going to say independent value to be asked, the dependent variable value to be asked. So I am going to go ahead and press second table, and now I'll start entering 4, which is my first value, and 3.5. Excuse me, I have to go back here to table set. The dependent variable is y, and I'll set it to auto and go back to table. It will compute the values of y now. So 3.5. The next would be 3.1, then 3.05, 3.005, 3.001, and you can see I started at a value of 34.3, and I'm slowly getting closer and closer to somewhere around 29.4. .405. So as t approaches 3, the value 3, the velocity approaches approximately 29.4. This would imply the limit of velocity at time t equals 3 is 29.4. That's what we mean when we say limit. So limit of a particular function, such as the velocity problem here or the tangent line problem, the limit of a function at a given value is nothing but the value the function would have as you change or bring the value of x closer and closer to the point that you're looking for. There are multiple properties to a limit, which will be discussed in the next video. Thank you for watching.